Hi everyone, Mr. Boltri here bringing you video 4.2 where we're going to be talking about impulse. So in this video, we're going to talk about what is impulse and then how to calculate it. Then we're going to connect that to the thing that we just learned, momentum, and then introduce the theory of conservation of momentum. So first, what is impulse? To introduce the idea of impulse, I have an example for you. We're going to watch two videos where we watch an egg drop onto a pillow and then onto the floor. And as you're watching this, I'm going to ask you to look at the two situations and think about, in terms of physics, why are these two situations different? Just so you know, the eggs were dropped from the same height onto two different surfaces, and the reactions are pretty dissimilar. And my question is, in terms of physics, why are these two things so different? So first, you can see me in the background. Hello, and thanks to Mr. Taylor for the help. But let's watch the egg drop into the pillow. Let's do that one more time, just in slow motion. Really let's focus in on that point of impact right there. So the impact, and you'll notice the egg stays intact. And it does a nice little bounce thing because it stays intact. It's not even worried about it, but I'm focused right here on the impact. Okay, so that's example one. And now we're gonna watch the slow-mo video of the egg dropping onto the floor. Okay, one more time. Actually, probably like a couple more times, just so we can focus in right on that impact time, right there. And so you'll notice a pretty different reaction, which was pretty difficult to clean up. But the question is, well, why is the reaction so different? So here I have the moment it's impacting the floor. You can see the crack already starting to form. And here the moment it's impacting the pillow, totally fine. So why are these so different? So if this was an ed puzzle, I would have the video stop and you could type out your answer. But I'm going to ask that you just pause the video and think for a minute before I go ahead and tell you. I want you to think, what is different about these two situations physically? So if we look at the situations, the biggest difference is the amount of time that it takes. So the pillow allows for the egg to slow down over a longer time period. It's not even that long. It's about half a second versus like just a tenth of a second. The actual times are a little bit smaller than that, but I sort of exaggerated this out a little bit so you could see the difference. So by giving the object more time to slow down, less force is required. And this is directly related to an idea of impulse. So in both situations, the same amount of impulse was needed. Impulse is the integral of force with respect to time. So you'll notice the area of both of these two shapes is the same. The shaded red area is the same as the shaded blue area. But if we give the object more time to exert the force, then it needs to exert less force to give us the same area. So more time reduces the amount of force. But then it might have you thinking, well, why do these two areas have to be the same? What physically says that these two things have to be the same? And we will come back to that as related to momentum. But first, if we just take this definition that impulse is the integral of force with respect to time, then we can easily write impulse, which is used for the symbol J. And why do they use the symbol J? I've done some research on this, and literally the best explanation I can find is that they would use the symbol I, but the symbol I was taken for moment of inertia for the I. So they just used the letter that was right next to I, which is J for impulse, which is fantastic and really easy to remember. But impulse equals the integral of the net force with respect to time. And I know you're probably thinking, well, wait, isn't the integral of force work? But remember, that is the integral of force with respect to displacement. If we integrate force with respect to time, then we get impulse, which uses the symbol J, which is not joules, by the way, which again, is just super fantastic and really easy to keep straight in your brain. So if we take the area of this, and that is the amount of impulse, which is a Newton times a second, which I guess you could simplify. You could get a kilogram times a meter per second, but that doesn't really have a super special name. So the only other special thing that I'm going to highlight for you about this is that, well, if you happen to forget your calculus, or maybe you are not given the function for this shape. You could do like a Riemann sum kind of thing and approximate the area. Or in some circumstances, you are given the average force, which this graph calls the effective force. But if we take the average force and multiply it by the time interval, then it should give us the same area as the actual force over the time interval. So this could be a useful way for you to back calculate the average force, is just by finding the area and then dividing by the time interval, which would give you the average force. Or sometimes you can find the impulse if you're given the average force by just doing the average force times the time. And notice here, we oftentimes use F for force. It technically is the net force unless you're calculating the impulse done by a single force, and then that single force would just be the F in there. So this is something that I know you already know if you're in BC, and I know that you will learn more in your AB class when you get there. But it just has to do with taking the average value by finding the total amount and then dividing by the change in time, and that'll give you the average. So we'll do some practice problems with this too. And now here's kind of the big deal with all of this. So if we take our formula for net force, which is Newton's second law over here, I know it looks different, but this is still Newton's second law. And then we take our formula for impulse over here, and you should maybe be noticing something by now. So impulse is the integral of force with respect to time, and force is the derivative of momentum with respect to time. So if we take our derivative of momentum with respect to time and plug it into our impulse equation, we get that the impulse is the integral of the derivative, which by some fundamental theorem of calculus, pretty sure we can figure out that the impulse equals not the momentum. Be very careful with this. Remember, when we take the integral, it's going to be final minus initial. So it's going to be impulse equals change in momentum, which this is huge. This is the connection between them. This is how it all ties together, and this is how it all makes sense. So if impulse equals change in momentum, let's go back to the egg dropping example. When the eggs were dropped, if they're dropped from the same height and they have the same mass, they're going to have the same amount of momentum right before they hit the ground, because they're going to have the same velocity, same mass, so same momentum. And if we want both of them to come to rest, then they both have to experience the same change in momentum. To go from their same mass and velocity to a mass and a velocity of 0 requires a change in momentum, and that's going to equal the impulse. So a certain amount of force exerted over time is going to be needed to slow down and stop the eggs, which is why these two areas have to be the same, because these two areas equal the impulse, which is how much the momentum has to change. So if the momentum has to change by a set amount, and we can go through and calculate this, then this is why if we increase the amount of time, then we can decrease the amount of force. By the way, this is just a rearrangement of one of the momentum equations that we had in our last video, which was momentum equals, or net force equals delta P over delta T, and just multiply both sides by the delta T. So if we have a set change in momentum, by increasing the time, we can decrease the net force. So if we increase the time by a lot, we decrease the net force by a lot, and then the egg doesn't crack. So this is the fact that the impulse equals the change in momentum is why increasing the time decreases the force. So I don't know. I just think that's really cool because impulse is kind of this abstract idea. It's the integral of force with respect to time until you figure out that it is the same as the change in momentum, and then you can do a lot of really cool, fun calculations with it. Okay, wrapping up the video, the last thing that I want to talk about is the idea of conservation of momentum. So we've said that impulse is equal to the change in momentum. And if momentum is conserved, that means that it changes by 0. So 0 change in momentum, 0 impulse. The only way that we can get 0 impulse, besides for obviously 0 time, but that's not so interesting, is if we have no net external force. And so this, or no unbalanced force. So the force is balanced, meaning everything cancels out. But this external right here, this word is actually doing a lot of work. Because what we're going to do is if we take, like, let's say 2 hockey pucks on frictionless ice. So frictionless would be an external force, but let's say it's not. And then they clank into each other. if we call one of the hockey pucks our system, then the other hockey puck hitting it is going to be an external force. But if we call both of them, if we say our system includes both of the hockey pucks, then when they hit each other and then go flying off, none of those forces are external because they are both part of our system. So then we can figure out the speeds and everything that at which the hockey pucks fly off using conservation of momentum, because there were no external forces, so there was no change in momentum. Which it just, and we're going to talk more about this in our collisions video, but this is a really powerful rule because momentum is conserved in situations where it might not even seem like it should be. Like in a collision like that, energy is lost due to the collision. So we can't use conservation of energy in our system. It's not lost, it's really dissipated to the surroundings. But momentum does not get dissipated to the surroundings. Momentum stays within our system like that. So it's going to allow us to do some really cool, powerful things. But the thing that you need to remember right now is just be on the lookout for situations in which the momentum, the change in momentum is going to be zero. And some clues for that are going to be if there's no net external force. So either all the forces are internal to the system, or there's just all the forces are balanced out anyway. So keep your eye out for that. And then we're going to do some practice problems with this too. So really cool momentum and its connection to impulse and how those two work together. I'm looking forward to doing some practice problems with you in our next class. But for now, this is Mr. Boltri wrapping up video 4.2, and go Bears.